Okay, so I wasn't going to record today, but I'm in a bit of a recording mood. So, um, today we're going to talk about register files, and this is not a register file. So I already have a MIPS register file over here. You can see it's big. There's a lot of watch state components in there. And I can show it. It's kind of messy. This kind of thing really wants the bigger custom components, which are coming soon. Um, so rather than just trying to, yeah, you can see how long it took to load. Rather than trying to explain what's going on here from scratch, because there's so much, we're just going to build a smaller register file, and you'll see the concept generalizes really easily to this kind of larger size. So we're going to build let's just call this RF. We're going to build a register file that has, I don't know, let's say 8, that's a pretty good number. 8 64-bit registers, and we're gonna make what's called a 2R1W register file. And what this means is 2 read ports and 1 write port, and we'll get into what that means in a moment. So just before we start actually building this circuit, I want to talk about the motivation for this kind of thing and what a register file is. So first of all, obviously for MIPS we don't need an 8 by 64, that means 8 registers of 64 bits each. We actually need a 32 by 32. But Turing Complete doesn't come with 32-bit components. As you can see, we have 64 and 8, and nothing in between. So 64 is just a little bit more natural for this demonstration, and since I'm only using 8 of them, this is going to fit pretty easily. Whereas when there's 32, like in the component that I just showed, it doesn't fit so nicely, and you have to do a little bit of work to make a custom that's a bit smaller than these. The other thing that I want to talk about is I want to talk about why you would want to do this in the first place. Like, what is a register file? What does it do? Why would you want to have one of these things? And so to do that, we're going to go look at leg, and I don't think leg is open in my sandbox, so I will have to switch, I think. I take it back. This is leg. Okay, cool. And what I want to focus on is, see if I can get the camera nice. Yeah, okay. What I want to focus on is this part right here, everything in there. So you can see I've labeled it with the comment at the top that this is a register file. And I didn't put this in a custom component when I was building leg because there aren't really enough registers to warrant it, and also the wire spaghetti level kind of tells you not to do that, which is unfortunate. So I just put it in line. But what you can see here, what's going on, basically, we have 6 registers, and you can see that their read lines are tied high, which means they're connected to a wire that's always on. And we're deciding which thing to actually use somewhere else, right? That's not a decision being made at the register level, that's a decision being made at the level of wherever the outputs are going. The other thing that's going on is they're each controlled by these write lines, and since there's only one register that can be written at a time, those are controlled by a single decoder. So if we could only read from one register at a time, we would probably also choose to do it with a decoder. So activate the read lines of the registers on the left side instead of selecting the outputs on the right side. But when you can read from more than one register at a time, it's more natural to do this, and the circuitry also ends up being a little bit simpler, right? Trying to coordinate reading from 2 registers at a time by just activating the right ones and then trying to get their outputs onto the right lines usually ends up involving a lot of circuitry. It usually ends up involving one decoder per register that you can read at a time, as well as one switch per register that you can read at a time. So in this case, we can read 2 registers at a time. There's 6 registers, except there's technically actually 8 because of input and the program counter. Although I don't think my leg actually supports reading from the program counter. But that's okay, because you never need to do that in leg. But yeah, so just focusing on the actual register components. Say there's 6 registers, you can write to one of them at a time, you can read from 2 at a time. So in order to do all of those things separately, you would need 3 of these decoders, plus 6 times 2 switches. So 1 switch per register per the number of registers that you can read at a time. And that's a lot of switches, right? And organizing that takes up a lot of space. So the key insight with a register file is that we can organize our registers all in one place and set them up so that all we need to know is which registers we want to read from, and then we can put all of their outputs into one multiplexer per register that we want to be able to read from at a time, and just send the address to each multiplexer, right? And so now if this top one says read from register 0, then register 0 will come out of this multiplexer, and that's completely independent, from what comes out of this multiplexer. So this multiplexer can be given 4, and it'll read from, register 4, 0, 1, 2, 3, 4. And you could flip those, right? You could tell this one to read from register 0, and this one to read from register 4, and the circuitry is the same either way, right? It's very simple, it doesn't matter. It's also pretty small. Wiring these parts in a clean way can be tricky, and it only gets harder as you add more and more registers. So this is one of those situations where it's very important to try and build in rectangles, use only straight lines as much as possible. And so most real architectures do this kind of thing. They would put all their registers together in one place like this, tie their outputs to a multiplexer, and this is called a register file. For MIPS, we're going to put it in a subcomponent because it's much bigger. In leg, it's fine if it's inline because there's only 6 of them. That works. So the other thing I want to talk about is what that 2R1W means. So, like I mentioned, that's short for 2 read, 1 write. And what that means is you can read from 2 registers at a time, and at the same time as you're doing that, you can write to a single register at a time. There are more versatile types of register files. So I think there's at least one project that's been done in TC so far that has a 5 read, 3 write register file or something crazy like that. So register files can get pretty big in practice, but in a lot of real architectures, it's pretty rare to see more than 2 write ports, although you'll frequently see a lot of read ports, like around 8, I don't think would be too abnormal. However, real-life register files tend to have a lot of registers for reasons that are beyond the scope of this series. If you're on an x86 computer, there's a pretty good chance that the register files on your processor have over 100 registers in them. So having 8 read ports is not so crazy when you have that many registers. But we only have 32 registers, and we can only execute 1 instruction at a time, and our instructions can only take arguments from 2 registers, so 2 read ports is all we need. And this is exactly that, right? This is a 2 read, 1 write, 6 register file. Except it's actually 8 registers, and oh hey look, you can read from the program counter. I missed that wire. Okay, so we're going to go build a similar version of that, but just with bigger registers, and make it a little bit more explicit what's going on. So first of all, each port requires a register address. So those are just bytes. So there's an A read port and a B read port. So these are addresses for registers, A adder and B adder. And then down here, there's going to be a write port, and each write port consists of 3 things, right? So there's a write address, there's a write enable, which controls whether or not you actually write at all, and then there's the write data. So that's the data that's an output. that's the data that's actually going to be stored in the register that's being written to. So actually it would be pretty normal to call this something like write enable like that. And so these are all the inputs, right? Each one of these is a single read port, and each group of 3 of these is a single write port. So 2 read, 1 write, that's all we want. The outputs are just the red values, and the red values are always on, right? If you choose to ignore them, you would ignore them from outside of the register file. So if you saw in leg, I was using a multiplexer to pick between the output of the register file and the immediate value from the instruction. So always reading the output of the register file, but then maybe ignoring it elsewhere if that is deemed to be relevant. So anyway, since these are read addresses, like I said earlier, if we wanted to decode these to pick the registers to read from and then get them onto the correct wires, that would be pretty annoying. But instead, I need a higher nesting depth here because we need multiplexers, right? So instead, we can use these multiplexer components, and I guess I only have these, but that can't be right. Sorry, like I said at the start, this was not a very planned in advance video. Okay, so we have these multiplexers. And we can use these multiplexers to pick the correct register to read from. So each one of these is going to be one of the outputs. So I'll take my address color. This one's the A output. This one's the B output. Okay. And now the rest of the effort for wiring up the outputs is mostly a matter of making sure that we stay organized so that things are easy to extend in the future if for some reason we were to decide that we want to do that. So each one of these wires should get its own dedicated row, which makes it, its own dedicated column, which helps keep things extensible. So I'm actually going to start from the bottom, just because I feel like I want the bottom one to be as close to these as possible. And already you can see I put it too far for this wire to go straight, so I'm going to move it back. And then this connects to the bottom pins. And then I'm just going to keep doing that. So for each register, this wire has to come up and stretch to 2 pins. One for the bottom multiplexer, the B read port, and one for the top multiplexer. And once we've done that, like we really almost have the whole register file. Like, obviously writing is important, but reading the registers quickly, that's really why we use registers at all instead of using RAM for everything. So this is really the important part to understand. How do you make a register file that is easy to read from? So one last wire. Of course, the writing is important, but okay. And so this already is a 2 read port register file. The only other thing we need for reading is we need to make sure that our registers are actually outputting their data, so that when we choose the right one to read from, we are, actually reading what's inside of it. So to do that, we just tie all of their read lines high. All right. Now similarly, just coming from the other side, the register is only actually going to care about its save value if the save enable is on, just like we're only going to care about the register's output if that register is selected by one of the multiplexers. So we don't have to switch the save value or anything. We can just send the save value straight through. I'm trying to pick a color. Use this one. We can just send the save value straight through directly to the registers. And why didn't I grab that? Like this. And if a register's write enable is off, then it's going to ignore the value anyway. So that doesn't matter. And then finally, in order to pick which register we want to write to, which one of these 8, this time we want to use a decoder. And that's because there's only one write port. This is much easier. If you have more than one write port, things can start getting pretty messy, and you actually probably want what's called a demultiplexer. I'm not the person to ask about that. I've never built a register file with more than one write port. Anyway, so one thing to notice here is that this address decoder is selecting 0 even when the write enable is off, right? That's bad. We only want to pick a register at all if the write enable is on. So we want to make sure that this decoder is disabled unless we're supposed to be writing. So it's very nice that the decoders have a disable pin. We can just run it up here. So now this decoder will only ever actually select a register if the write enable is on. And that's actually the only thing that this write enable has to do, right? The write enable doesn't have to be tied to the write enables of the registers because these write addresses will be. And so we can just send these straight over to these pins. Very smooth. You could probably get it to look a little bit nicer by, not doing that, by putting these wires on the far side of this gap, so putting them over here instead. But this is fine for our purposes. This is just a little bit faster to build, so use that. That's unfortunate placement. Alright. So there we go. And that should be the whole register file. So we could try and test this. There's a couple of bugs with the component factory at the moment that... Oh, never mind, this has been fixed. Awesome. Okay. It used to be that when you flipped bits on the 64-bit input pins that they didn't actually show. But this is great. Okay, this works. So right now we have write address 0. So if we flip the write enable, this top register's saved value changes to 256. And on the next tick, since both read ports are addressing that register, these are both going to switch to 256. So that's perfect. If I change one of them, you can see now it turns to 0 because that's what's in register 4. And I can put this one on 8, I guess that's fine. Oh. So this is indicative of a problem because... yes, of course, because 8 is not actually an address, right? 7 is the furthest address. So now it's pointed at this register. So now we could write into one of the ones that neither of these is looking at. So I don't know, let's write into register 2. Let's give it, I don't know, the byte of all ones. You can see now that's stored in here. We could change this to look at register 2, and all of this works exactly like you'd expect. We can go write something into register 7, and what do you know? Now it's coming out of the B line. So this is a very extensible sort of framework for building register files. It's very useful in practice, and the MIPS register file looks exactly like this. Now there's one catch. On RISC machines, reduced instruction set architectures, sort of generally you want to make the common cases of instructions as fast as possible. And it turns out that for a variety of reasons, it is extremely common for 2-argument instructions for one of their arguments to be the number 0. Super common, something like 25% of all instructions in a program or something like that. Something crazy, I don't remember. More than you would expect because these instructions tend to get executed more often, like they tend to be in loops and stuff like that. So in order to support that, most RISC architectures have a register file like this, except usually with 32 or 64 registers, more than 8. But the bottom register, the register with address 0, is not a real register. And instead, what you have is you just have the constant 0. And it doesn't do anything. It's not really there. You can't write to it. You can't store numbers inside this constant. But you can read from it. And so whenever I put these addresses to 0, I know absolutely certain that the outputs are going to be 0, right? No matter what's in the other registers, I'm always going to get 0. And if you try to write to it, then the write just gets discarded. And doing that inside the register file makes life much easier for the decoder, because the decoder doesn't have to know the destination address, right? It doesn't have to know that, hey, this instruction is attempting to write into the 0 register. I need to throw that right away, right? I need to turn the write enable pin off. The decoder doesn't have to care about that. It can turn the write enable pin on if it wants, because what happens when we try and write to address 0? See, this line comes on, but it's not connected to anything. So this is perfectly fine. And so this is a sort of general design principle called separation of concerns. You'll usually hear it in software contexts, but it applies to hardware too. So by specifying that this register should be hardwired to 0, that's a statement about the register. We should build that functionality into the register file instead of trying to build it into our instruction decoder. So anyway, this is a pretty straightforward 8 by 64 register file. These multiplexers are nothing special. In the first part, we talked about how to do these for 1-bit values. These are exactly the same, except they work on 64-bit MUXes. Their labels are 32 because MIPS is a 32-bit architecture, and that's what I built them for, but inside they're just using 64-bit multiplexers like this. And it's exactly the same idea as for the 1-bit ones. So anyway, yeah, that's the whole register file. We can look at what I did for MIPS again. And with this view of register files, it should now be a lot easier to see what's going on here, right? It's just exactly the same thing, but on a much bigger scale, right? So because we can't fit 32-way multiplexers into a single column, I mean, we actually could, but we couldn't fit them into a custom component because there aren't enough pins. Each read port has 4 of them. So this is an A read port, this is an A, this is an A, and this one is also an A, the ones with the pink wires. The ones with the purple wires are for the B read port, and then there's 2 further multiplexers to select the correct value from those. And you can see the controls for these multiplexers are coming from the 4th and 5th bits of the register address. Other than that, it's exactly the same thing. So we're basically using a multiplexer tree to construct a 32-to-1 multiplexer. You can see right here, this bottom register is hardwired to 0. Now for silly reasons about the wire routing, I decided it would be a little bit easier if this top set of 8 registers was stored backwards. So this is actually register 0, 1, 2, 3, 4, 5, 6, 7. But then after that they go in order, and I use the color scheme to help myself keep track of which ones are which. So this dark orange color is always the bottom register in each set of 8. The pink color is the next register up, then purple, then blue. And I just went in the order of the colors in the menu over here. The other thing that's going on is on this side, the read ports. And you can see this is exactly the same idea that we were just talking about. It's just that now there's more options. And because we need 5 bits of control, but we only have 3 to 8 decoders, we have to build a 5 to 32 decoder out of 3 to 8 decoders. And the way to do that is you use one of them. So this bottommost decoder here, you can see, is using bits 4 and 5. If I can highlight them. Just bits 4 and 5 of the write address to pick which group of 8 registers to look at. So that's either this group, this group, this group, or this group, right? And then for each one of those groups, it gets its own 3 to 8 decoder. So here's the one for the bottom group, for the next group up, etc., etc. Those decoders have their disable pins attached to the disables of this attached to the values of this decoder. Right? So we're always disabling the decoders unless the block selector, that's what I call this decoder. Unless the block selector says, for example, that we should use block 0's disable pin is going to be on. So in this case, the write address is 0, so and the write enable is on. So it is saying that we should use block 0, and accordingly, its decoder is on. However, you can see that that pin, this one, is not connected to anything, because this is just a constant over there. And it's a byte constant because that's easier to fit in the space, but of course it's attached to a 64-bit wire. So if we turn off the write enable, you'll see the disable on that decoder comes on. And so this is just exactly the same thing that we just built in much bigger fashion, right? It's just a bigger circuit. There's all these watch memory things, like they're all connected to exactly what you would expect them to be connected to. Or actually, I guess maybe they're not because of the patch earlier today, so I probably have to fix those, but at any rate. And then inside these register components is exactly what you would expect, right? It's literally just a 64-bit register combined with this thing to make sure that we're only storing 32-bit values because we're building a 32-bit machine. And, oh, but that one's still connected. Interesting. So yeah, this is register files for MIPS, and next we will build the decoder.